Our next speaker is Bart van der Vecht. The stage is yours.
All right, so it seems to be working. All right, good morning, everyone. Thank you for having me. So my name is Bart van der Vecht. I'm a PhD student at QTech in Delft. And so the topic I would like to talk about is application programming for the quantum internet. And so when I say application, I really mean any kind of quantum network application. So this can be QKD, but it can also be beyond that. So like distributed quantum computing or remote access to quantum computing. And also in general, my talk will be a little bit more high level probably than most presentations so far. This is because I'm not a physicist, I'm a computer scientist. So I'm kind of in a position where I assume that the physicist will somehow solve these difficult hardware concerns for me in general. And I can kind of assume that, for example, things like entanglement generation is already available as a service. And I think more about the software that we built on top of that and to use that to program applications. Yeah, so a quick introduction. So as I said, I work at QTech as a PhD student. I'm in the quantum internet division. And in this quantum internet division, we have actually many people with different backgrounds working on different things. So some people are physicists and experimentalists, so they work on hardware. We have a setup in the lab where we can do experiments with 2 or 3 quantum network nodes based on NV sensors and diamonds. But there are also people in the division that work on simulations of the quantum internet, people that think about repeaters, repeater protocols, placement of repeaters. And then there are people, including me, that think about software that runs on quantum networks. And so this is software that controls nodes in a quantum network, but also we think about expressing quantum logic in software. So if you have an idea about some protocol, quantum network protocol, how to express this in software and actually run it on a quantum network. And so specifically, one of the questions we asked and that I also personally dealt with is how to write arbitrary high-level application code and execute it on a physical quantum network node. So currently with the standard internet, in theory, basically anyone could think of a new kind of application and they could program it and then run it on the internet as is. And the idea is that if at some point we have a quantum internet that also consists of quantum computers that are connected, so if you have an idea for a new quantum network protocol, how would you then express the logic for this protocol, write it as program code, and how to execute this on a real quantum network? So to this end, we have developed something called NetQASM, and this was also something I also showed on the first slide already, but I kind of skipped over it. But so NetQASM is something we have developed and implemented. And it's basically a low-level language that is used to interface with nodes in a quantum network. And I'll show some examples later. But on top of that, we also created a Python SDK, SDK standing for Software Development Kit. So this is some software that allows programmers to write application code in Python and then have it be executed on a quantum network. And not only did we implement this software, this NetQASM and this Python SDK, we also connected all this to our setup in the lab. And we used NetQASM to run an application, simple application for now, but on a real hardware setup. So the model that we use for a quantum network is quite high level and abstract. So we consider a network consisting of nodes, and these nodes are programmable. So these nodes consist of some classical processing unit, which can execute arbitrary classical code, but also a quantum processing unit consisting of quantum memory, and it can do arbitrary quantum gates and measurements. And these nodes are all connected both by classical communication channels, so they can send messages to each other through the normal internet, basically, but also they can, of course, generate entanglement with each other. An application in such a network is a multipartite protocol like QKD, but it can also be distributed quantum computing or something called blind quantum computing, which is basically a secure delegated computation in a quantum network. And such an application, for it to run on a quantum network, each of the nodes that participate in this multipartite protocol should somehow run their own code on this programmable node. And so I will call a code like a program for I will call code for a single node a program. And so the rest of this talk will be about how to express such a program and how to execute it on a quantum network node. And so we consider programs for quantum networks we think they can consist of many different types of operations. So these programs may want to send or receive classical messages from other nodes, but they might also want to generate remote entanglement. They might want to do some classical calculation just locally, or they might want to do some local quantum gates and measurements. And so all these kinds of things should be expressible in the program. And also all these kinds of operations should be able to be interleaved and depend on each other. Another thing I should mention is that within QTech, we are envisioning like an abstraction hierarchy for the quantum internet. So we have this layering based on the TCP/IP stack, basically. And so the idea is that each layer has its own concerns that it has to deal with, but it hides complexity to the layer above. So the physical layer. So like the lower layers are there, for example, to generate entanglement between two links that are connected directly. But for example, the network layer is there to provide an entangled link between any two points in a network. And so if you want to know a bit more about these lower layers, there are publications from QTech about this. So there are some titles there. But in this talk, I'll talk about NetQASM, and this is actually an application layer, so very high level, very abstract. But the idea is that applications, so programs, can use this network stack. So the idea is that each node in a quantum network implements this network stack. Most of these layers are actually the software layers, and so programs should be able to use this network stack, for example, to create remote entanglement. So if you have somehow a program for a node in a quantum network, how would you execute this? So the model that we use is basically similar to quantum computing. So in quantum computing, the idea is that you can just run classical code on a normal PC, run normal CPU, for example. But if you have some quantum code that you want to execute as well, then you kind of bundle this quantum code in a quantum circuit and you send it to a coprocessor or a quantum processing unit. And this quantum processing unit then executes this quantum code for you. And at some point, it's done processing all these gates and these measurements, and then it returns control back to the classical processing unit. And then, okay, so yeah, so we have this conceptual distinction between the application layer and the quantum processing unit. So in our implementation, these are also actually two separate physical devices, but they don't have to be. And the idea is that programs running on a quantum network node, the classical parts run in the application layer. So unlike, you can think of it as runs just on the classical processing unit. And also this layer is responsible for using the standard internet to send and receive classical messages. But any quantum related code is dedicated to the quantum processing unit. And this unit implements the quantum network stack. So it houses the network layer and the link layer, for example. And so program code can send requests to these layers to do, for example, entanglement generation with other nodes in the network. But this quantum processing unit can also just do local operations on the quantum memory, like doing gates and measurements. And so these two layers, these two components have to work together, and they do so via NetQASM. And so whenever the program wants to delegate certain computations to the quantum computation to the quantum processing unit, it does so by bundling quantum instructions into a block of NetQASM code. And in the next slide, I will show an example of how this looks like. And then the quantum processing unit executes this NetQASM code. And one thing I want to point out is a difference with quantum computing. So with quantum computing, whenever you send a block of quantum code to the quantum processing unit, and when this block has finished executing, all the quantum memory is being reset. Basically, at the end, all the qubits are being read out, and then measurement results are sent back to the classical processing unit. With quantum network codes, we also, what we sometimes might need is that the application layer sends a routine or a block of NetQASM code to the quantum processing unit. At some point, the quantum processing unit is done executing the quantum code and sends the results back. Maybe then the application layer does some classical computation or some communication with other nodes. But meanwhile, we may want to have the quantum memory actually stay there in memory, and then later on we get back to it with some new quantum code acting on this memory. So an example could be that a program first generates entanglement with a remote node. It stores the entangled qubits in memory. Then it does some classical communication with other nodes. Maybe it waits for a message from another node saying what it should do, and only then it gets back to the quantum processing unit and acts on these quantum memory locations again. And maybe then it does a measurement on this qubit. So this does mean that quantum memory needs to have pretty long lifetimes. In our case, we have implemented this on NV sensors in diamond, and qubits in there have actually pretty long lifetimes in the order of milliseconds, even seconds. So this is actually possible. So how does NetQASM look like? I will just go briefly through this, but if you're familiar with programming or assembly languages, this might look a little bit familiar. Also, if you're familiar with quantum computing and programming for quantum computers, you might know OpenQASM, which is a low-level language for programming quantum circuits. And NetQASM is similar to OpenQASM, but of course it has these extra instructions for entanglement generation. So we have this create EPR and receive EPR for two nodes that want to engage in entanglement generation between each other. Also, we have wait instructions, because also in contrast with quantum computing, we might not know how long entanglement generation takes. So for example, on the right here, there is a create EPR instruction, but then we have a wait instruction, and this wait instruction basically says block until this entanglement generation is finished. So if you want to write a program for a quantum network node, you don't have to write NetQASM immediately. You can actually just write your code as Python. So we implemented this software development kit, and it allows you to write your code just as a Python script. So on the right, you see an example there. And then the relevant parts are automatically being compiled to NetQASM routines and being sent to the quantum processing unit. As part of this SDK, we implemented a simulator. Actually, you can use two different simulators. So one of them is Simulacron, which has already existed from QTech. Has already existed for some years, and we created a new simulator as well called SquidASM. It's based on NetSquid. And these simulators really simulate the quantum network, including the quantum network stack that we have designed as well. But not only can you run your programs on a simulator, you can actually run these same programs, so also written in Python, on a real hardware setup. So what we did, we connected the NetQASM SDK to our lab, in which we used two quantum network nodes based on NV sensors and diamonds. And basically, we showcased that you can write a program in a very high-level way. So as Python code, on the left, you see the code that we used. And this code was automatically compiled to NetQASM subroutines, and it was automatically being executed on the quantum network nodes. And so this application just created entanglement between the two nodes. And in this way, we showed that we can actually run an arbitrary quantum network program, even though we specified it at a very high level, it still works with actual quantum hardware. Another thing I want to briefly mention is that we created this thing called the Quantum Network Explorer. So it's a website, quantumnetwork.com. You can go there right now if you want. And basically the idea is to kind of engage people and teach them about quantum networks. So you can find information on the website about what can you do in general with quantum networks. But another thing that we did is we have some applications on there written using the NetQASM Python SDK. And you can actually run these applications on the website, and they are then being simulated on our backend. But you can see visualizations of these applications running. And so you can really see what's going on. So you can, for example, run a QPD application or a teleportation application, and then you have these nice visualizations showing what's going on. The idea for the future with QNE, with Quantum Network Explorer, is that you can also use the NetQASM SDK to write your own programs and then upload them to our website, also have them simulated. And what's more is that at some point, we hope to actually connect our own hardware, the quantum network hardware, to this website as well. So that at some point, pretty much anyone can write their own quantum network application, and then through this website can run their code on our actual quantum internet hardware. So that's, I think, quite exciting. Very briefly, Outlook. So like the way, so I kind of showed you that we have this distinction between the application layer and the quantum processing unit, which can be kind of slow because sometimes you have to send these NetQASM code from the application layer to the quantum processing unit. And so there's definitely some improvements to be made there. Also, the automatic optimization of such programs is not really looked into much. So there's a lot of things to do there as well. And finally, what I already mentioned, we want to connect the Quantum Network Explorer to our hardware so that this quantum internet really becomes available for everyone, pretty much. So just quickly to conclude, so NetQASM is a language and an interface to control nodes in a quantum network. You can use it to program and run arbitrary quantum network applications. You can actually use a Python SDK to simplify writing code. So you don't have to write these NetQASM statements, but you can write your code using Python. You can run this code then on simulators, but also actually the same code you can run on real hardware. So we already showcased this in the lab. And in the future, we hope that everyone can do this on publicly available quantum hardware. Finally, I just want to thank people that worked on the design and development of NetQASM. I do also want to mention that even more people have been involved with this integration with the hardware. So also many thanks to them. And finally, thanks to you for listening.
We thank the speaker for the interesting talk. Now move to the organizer's question. What do you think will be the main use case and then the main challenges for entanglement-assisted communication networks?
So I think the main use case for quantum networks, also including quantum computers, will be something called blind quantum computation. So this is basically remote, so delegated quantum computation. So imagine there's a server which has a large quantum computer, and then clients can connect to this server, and they can delegate quantum computations to this server, but in such a way that the server actually doesn't know what computes for them. So therefore, it's a blind computation. But in this way, many people can actually use these larger quantum computers, which are maybe not, they do not exist very much yet. Only maybe a small number of companies have a large quantum computer, but then people can use this quantum computer in a dedicated way. I think the first use case would be to use entanglement to delegate these quantum computations to the big quantum computers. So the challenges, so definitely one of the challenges is just to be able to do remote entanglement generation over long distances. But also specifically in my field, actually about software, there are definitely challenges about, I briefly mentioned this already, how to express this code. So currently we have this division between classical code and quantum code, and it's quite inefficient to switch between the two. And so I think there are definitely some challenges in improving that.
Okay, the last question is, which possibility do you see for quantum technology to contribute to 6G networks?
Yeah, so to me, 6G is still kind of a vague concept. So I think in the mobile area, I don't really see a direct contribution from quantum. But in general, I think it is very promising to kind of add quantum computers to the internet. So maybe if 6G can somehow, one of the things of 6G can be that we integrate quantum computers with the whole network. And then I think that is a useful new thing of 6G.
Thank this speaker again. Thank you. We apologize for all the technical difficulties. Now we move to the coffee break.